All right, so today we'd like to discuss about the oxygen evolution reaction to produce uh, the hydrogen from the water. Not surprisingly, we already discussed that we definitely dissociate the water, right, to produce the oxygen for the counter reaction of the hydrogen evolution reaction. So today we will discuss about how to dissociate water to the oxygen in high potential the region for we call it as a oxygen evolution reaction or just OER, right? So in this chapter, I would like to highlight that the importance of the balancing between the activity and the stability. And I would like to introduce that one of the strategy, actually there are lots of the strategies. So I do not want to mention that this is the best way, but this is the one of the ways how to approach that the activity and the durability the simultaneously. So today we would like to discuss about oxygen evolution reaction, starting from the acidic media. So let's think about that. What about the activity and the stability in OER in acid media for the PEMWE? So not surprisingly, many researchers dive into the which material is good for the activity and the durability. So please think about that the overpotential, which indicates that the activity of the OER. So the lower the overpotential means that the higher the activity, right? So as you can see, the osmium, ruthenium, iridium, platinum, the gold shows that the following reaction. The best one is the osmium, but not surprisingly, if you check that the durability, that the dissolution of the noble matter during that the reaction condition, the dissolution is really high in the case of the osmium. That's the reason why we do not consider the osmium in general. So what about that the ruthenium? As far as I know, the ruthenium can be really popular recent day because people would like to replace that the iridium system with that the lower the price material because that the iridium is really expensive, right? But anyway, please keep in mind the ruthenium is good candidate if you focus on to the activity. Please compare the ruthenium and the iridium, right? But please keep in mind that the dissolution is much significant in the case of the ruthenium. That's the reason why people conceive the idea that the iridium is the relevant catalysis for OER in PMWE because it shows that the relatively high activity and also shows that the relatively good stability, right? That's the reason why iridium has been considered as a benchmark for the OER electrocatalysis. What about the platinum? Platinum shows that the much less activity compared to iridium, and even though it is relatively stable during that the reaction condition, but as you can see, it is not a good idea, right, to utilize that the platinum because that the activity is really low compared to the iridium system. That's the reason why iridium is good. So if we discuss about trend of the activity and the stability, but please keep in mind the discussion for the stability in this chapter, we will only narrow down that the dissolution of the metal, right? So anyway, if you focus on to the activity of the oxide, it follows that this trend, gold, platinum, iridium, ruthenium, osmium, and what about that the stability trend? The dissolution trend shows that the exactly opposite, right? The higher the activity shows that the lower the stability, right? So people figure out that there is the certain relationship between the activity and the stability, right? So this is the case study of the monometallic system. And if we move to what about that the surface, the structure effect? I believe you're already familiar because we already discussed about that the structure function activity relationship in oxygen reduction reaction. And we discussed that there is a certain the trend depending on the surface facet, right? So in these cases, we would like to just fixing the materials as a strontium luteinate, right? But the difference is the surface facet, right? So we would like to compare that the three different cases. One is the strontium lutenate 111 and 110, and the final is the 001, right? So please keep in mind that the major, the purpose of this study is to figure out that what about the structural effect for the activity and the stability, right? So we would like to discuss the results directly. As you can see, the higher the activity, the platinum, strontium lutenate 111 followed by the 110 and 001. So you can easily check that the activity trend just to read at the current density, right? And what about that the stability? If you quantify that the dissolution during that the reaction condition, then you can also easily quantify the stability trend. Interestingly, the higher the activity shows that the lower the stability. But we already observed in the case study one under that monometallic system, right? So people figure out that now there is still certain trend between the activity and the stability, right? That during that the reaction condition. So for the confirmations about that stability, people figure out that how the surface can be collapsed or reconstructed by the dissolution during the reaction condition. So we will discuss later for the in situ, right, analysis to figure out that how the structure is, right? And so people confirm that during that a certain period of time, people figure out that how the surface can be collapsed or changes, right? So if there is no change, not surprisingly, we can definitely say that the surface is stable or unchanges, right? The higher the changing means that there is a huge reconstruction or dissolution or something like that. So if you figure out that how it can be easily changeable, then we can definitely say that it is unstable. Not surprisingly, in the case of the strontium lutenate 111, it shows that the significant fast reconstruction compared to the other surface, which indicates that there is still a trend between the activity and the stability, right? So let's think about that. What about that bimetallic system, right? So please let's go back to the slide over here, right? Over here, right? We already compared that the two different cases with one with the ruthenium and the other one is the iridium, right? So if we only focus on to the activity, right, the ruthenium is better. But if we compare that the stability, iridium shows the higher, right? So the people conjecture there, what about if we mix the ruthenium with iridium, for example, the alloy structure, can we overcome the activity and the stability? This is the questions people would like to discuss because that at this time, 2014, around the 10 years ago, people would like to still figure out that is there any relationship between the activity and the stability, right? So let's think about that, what happened if we make a ruthenium iridium oxide as a alloy, the bimetallic cases for the discussions about that the activity and the stability, right? So to make a long story short, the researchers discuss about two different methodology to prepare that the bimetallic oxide. One is the TC, means that the thermal chemical oxide. It is so simple. After the deposition of the ruthenium and the iridium as a sputter, they anneal the high temperature. So this is the high temperature annealed sample. And EC oxide means the after depositing ruthenium and iridium, people just make hydroxide and oxide by potential cycling. So this is the electrochemically driven the oxide. So I do not want to discuss in details what makes differences for the in detail, but please keep in mind that. Please think about that over potential in here, right? So there is a certain trend between four samples, right? By changing that the ruthenium and the iridium. And what about that the stability? If we confirm that the dissolution, right? There is an inverse trend, right? The higher, right? The shows that the the lower the stability, which means that there is a certain cap for the activity and the stability. So people conjecture that it looks like there is a relationship between the activity and the stability in general, right? Because that we compare that the three different model study. First one is the monometallic system by just comparing that the different metal as a candidate for the OER catalysis. The second, we discuss about what about that the surface effect, the structure effect, by the maintaining that the same materials as a strontium glutenate. And we also figure out there is a rule for the activity and stability. And the last cases we discuss about that mix and match between the one and the other. And it shows that if we make mixing with two materials, it shows that uh, the average property, right? So if we compare that the ruthenium and the iridium, what about that the activity of the ruthenium iridium? It shows that the in between of the ruthenium and the iridium, right? What about that the stability? It shows that the still under the rule between further activity and stability shows it just shows that the average the property, which is not a good news for us because that our major the discussion is there any possibility to overcome that the activity and the stability, right, trend? So, not surprisingly, people aware that in acidic media, it is not a good idea to design that electrocatalysis because if you design that a high activity the catalytic activity, but we always pay for the stability, right? That as the rule of the activity and stability. But I would like to highlight that it is the rule of thumb because even though we observe that the many trends, but it is not directly the validated or the verified by the theory or the experimental section, right? Because we only discuss about that trend between the several case study. So we have an idea that there is a something rule of thumb of the inverse trend between the activity and the stability in acidic media, right? So people would like to dive into the alkaline media because people conjecture that in alkaline, people think about that it is relatively good for the stability. So not surprisingly, please keep in mind that when we discuss about monometallic system, we only discuss about that the osmium, ruthenium, iridium, platinum, gold, something like that. What is the platinum group metal, right? But if we move to the alkaline media, not surprisingly, we can utilize that the 3D transition matter, for example, the nickel, cobalt, or iron, or something like that. So it is a really good news for us because we can utilize that relatively cheap materials, right? If we focus onto the alkaline media, and the activity is really good compared to the platinum group metal cases, right? And so this is the reason why the many researchers move to the alkaline media for the choice. There is a lots of the possibility for choosing that good materials for the OER, right? And so we would like to discuss about that alkaline OER in detail. Uh, what happened, right? So the key idea is people figure out that nickel is the best catalysis for the OER in alkaline media in general. Before the 2000, maybe 14 because this paper is really important, right? Because before the 2014, the people believe that the nickel shows that the highest activity compared to the others. So a lot of the researchers has been focused on the why the nickel is the good materials for the OER. However, please keep in mind that in 2014, there is a really important paper in the Alkaline OER Society, right? So please keep in mind that all the samples are utilized to the pure nickel hydroxide without that iron in the material itself, right? So what happened for the activity and the stability the trend of the system? So this is the first case when we utilize the nickel hydroxide, right? But please keep in mind what is the difference? It shows that the quality of the salt to prepare the potassium hydroxide, right? Now, surprisingly, if you make a 0.1 mole or 1 mole potassium hydroxide solution for the alkaline electrolyte, you definitely dissolve the salt of the potassium hydroxide. And not surprisingly, we already familiar that there are lots of the different grades, right? So for example, the trace select grade, the reagent grade, and if we handle that the purification of the potassium hydroxide, the activity trend shows that the totally different, right? So what happened? If we directly use without further purification, for example, using that trace select basis, the concentration of the iron as an impurity in KOH shows below there a certain ppb level. And what about that the reagent grade, which is the huge amount of iron, even though the one ppm, but 1 ppm is not that small, so there are a huge impact for the activity, right? So please keep in mind that if we utilize that low grade KOH, potassium hydroxide, it shows that the higher the activity, right? Now, surprisingly, the activity is governed by the amount of the iron in electrolyte, right? So this is still really striking because if we purify the electrolyte, right, to remove the iron in the salt, the activity is negligible. Please keep in mind that the activity and the trend, right? So when there is iron in impurity, the potential is the 0.305. It shows that the current over 4 like this, right? What about the 0.305, this region, right? Actually, if there is no iron in electrolyte, there is no any activity, right? So this is the really important that the lot of the study has been contaminated by the certain amount of the iron species during the electro during the OER, right? So even though you prepared the nickel hydroxide as a pure hydroxide or pure metal or pure oxide, the iron in electrolyte can contaminate your surface and it generated the nickel iron, right? So this is the really striking and very important, but please keep in mind that this is not suggested by the 2014. It is re-highlighted in 2014, but the interesting feature is the original paper that the importance of the trace amount of the iron to make a huge the activity trend was already reported in the 1987, right? This is the really striking, right? But the funny things is, as I mentioned that before the 2014, the papers are published that sorry, before the 2014, the citation is almost negligible, right? But please keep in mind that after publishing data checks in 2014, the original papers are also highlighted, right? So this is a really ridiculous because that even though it is the original discussions about that, the importance of the very small amount of the iron impurity can change that overall trend of the activity, but people do not aware of that, the importance of that kind of the impurity until 2014. This is a really striking. So, but anyway, if we revisit the original paper once again, the feature is exactly the same what we observed, right? If we control the iron in electrolyte, for example, if we remove or control that impurity in the electrolyte, the activity is negligible. However, the 1 ppm is truly enough to activate the system, which means that even though we prepared the nickel hydroxide or nickel-based materials, if you immerse the system without purification, it can turn out to be a nickel iron system, right? So the key idea is that trace amount of the iron is really important for activity in OER, right? So after 2014, people aware that, right, that the iron nickel is the best, right? the nickel itself, the activity is not that good, and iron itself, the activity is still not that good. And if we prepare that the nickel iron or accidentally prepared by the nickel iron without further purification of the electrolyte, people figure out that the nickel iron is the good catalysis for the OER, right? And what about that the remaining things, right? The remaining things should be that discussions about where is the active site, right? So to think about that, people figure out that there are two studies. There are so three model. One is the just I'm sorry, I think it's much better to there are three surface. One is the nickel, and one is the iron, and the other one is the nickel iron, for example, right? And the activity of the nickel iron is much better compared to the nickel and iron, respectively, which means that we don't know actual what happened, but the nickel iron is the active site, right? And people figure out that where the real active site is in atomic and molecular level, and there are three scenario, right? So let's dive into what the three scenario means that we would like to focus on the nickel iron. The first scenario is nickel is the active site, but iron promotes, right? So that the iron promoted nickel is the active site. This is the first scenario. The second scenario, not surprisingly, which one? Iron is the active site, but iron itself is not activated, which means that nickel promoted Fe is the active site for the OER, right? And what about that? The last cases, there are certain surface with the one nickel and one iron shares that the active site, which means that they're perimeter, right? So if we draw that the nickel atom, and if we draw that the iron atom, the interfaces between the nickel atom and iron atom as a co-catalysis for OER, right? So not surprisingly, there are three scenarios, right? Nickel, iron, and in between, what is the real active site? This is the very important the field to discuss, because not surprisingly, we definitely need the recipe, how to increase the activity, right? To know that the recipe, to get the recipe, the first step is to find where the active site is, right? So people figure out that the various important in situ analysis. In 2015, people figured out that some groups propose that iron 3 plus is the active site. The other group shows that iron 4 plus. The other shows that, oh my God, I'm sorry, there are four cases. Oxygen is the active site, not the transition matter itself. I will discuss shortly later. But anyway, the active oxygen can be considered as an active site. What about 2016? Nickel 4 plus has been proposed, and also iron 4 plus. What about 2017? The oxygen revisited again, and the nickel 4 plus and nickel 4 plus, right? So please keep in mind that I don't want to say that which one is true and which one is wrong, because it is really hard to say. I believe that everyone and everything is good and true, but please keep in mind that those papers are published at almost all of the good papers in Jackson and Angewandte Chemie, right? The Nature Chem or PNAS, right? So something like that. So this is a really nightmare. No, nobody knows that where the real active site is, right? So let's think about that, the brief summary, what the people that discuss, right? So due to the time limit, we do not want to discuss in details, in every details, but people figure out that people propose that the very well-controlled system to figure out that where the active site is. So people discuss that some group Fe and the other also Fe and nickel or the Fe. This is a really hard to say that which one is active site, but people figure out that there is a lot of the possibility, but nobody knows that where the really active site is, right? So this is the reason that I would like to dive into when I start the postdoc career, because I studied my postdoc in the end of the 2016, actually 2017, right? So this is the summary. But actually, when I prepared that the strategy to dive into the research, because I believe you already do the same way, right? When you start at the new field, you definitely find that good review materials first, and then you definitely focus on to the or what people already mentioned or discussed before. So I realized that there are huge controversies between the groups. So I would like to jump into the study, how it looks like. So my supervisor at the time proposed me that uh, do not think about the mechanism, but just to focus on to the activity stability trend in alkaline media, right? So before we go any further, I would like to revisit that trend what we discussed in the acidic media, right? So we confirmed that based on the previous study. People are aware that nobody knows in details, but the rule of thumb, it looks like activity stability inversion trend, right? In acidic media. So my supervisor asked me about uh, to figure out that is there any relationship in alkaline media, right? So I would like to dive into the system with the monometallic system because this is the easiest way, right, to compare that. What about the trend between activity and stability? So I do not want to discuss in detail, but to make a long story short, I prepared that the three samples with nickel, iron, and cobalt, right? And it follows that the iron shows that the higher activity and the cobalt and the nickel followed, right? And also, I'm truly working with the ICP mass to quantify the dissolution during the electrochemical analysis. So this is the really in situ data to monitor the dissolution during the oxygen evolution reaction. So we can easily, frankly, not easily, but anyway, we can count that. How many atoms can be dissolved during that potential cycling, right? So if we quantify the dissolution during the reaction, the iron shows the highest dissolution compared to the cobalt and nickel. And surprisingly, even though it is not allowed to say that we found there is a rule because I only compared the three samples, right? But anyway, I confirmed that it looks like there is still, right, inverse trend between the activity stability in the alkaline, the media, right? So the iron shows the highest activity and followed by cobalt and nickel. And what about the stability? Nickel is the most stable and followed by the cobalt and the iron. And I realized that, oh my God, this is a really interesting because as I mentioned that, we would like to discuss about where the active sites about the nickel and the iron, right? So I conjectured that if I confirm that, if there is still the activity and stability relationship in alkaline media, uh, I can solve the problem for the active site because if I compare that the nickel iron, right? And if there is a iron dissolution, then the iron is the active site. And if there is a nickel dissolution, maybe the nickel is the active site, right? So I make a very simple assumptions that if I can figure out that activity stability relationship, I can solve the problem for where the active site is in alkaline media, right? So after discussions about that, the very brief discussions of the activity and stability trend using the monometallic hydroxide, I jump into the bimetallic system because people already figured out that iron nickel and iron cobalt is much better compared to the iron, cobalt, and nickel itself, right? So I prepared that the similar way to prepare the iron nickel and iron cobalt and do the stability analysis as in the figure. And I'm really surprising that just 1 hour is enough to deteriorate all of the surface, right? For example, at the very beginning, iron nickel shows that the really high activity, this is the current density, and if we compare after 1 hour, the activity is gone, right? What about iron cobalt? Even though that it shows that the high activity at the beginning, but the stability is really low, right? This is really striking because that most of the work already reported that the iron nickel and iron cobalt is a really stable electrocatalysis during that water electrolyzer. So I really struggled about that. What is the differences between my study and the others, right? And I realized that, as I shortly mentioned, that at that time people are aware that a certain amount of the impurity makes a huge trend and huge impact for the activity, right? So I spent almost 6 months is to prepare that iron purified electrolyte. And I realized that nobody discussed about stability analysis using and that purified potassium hydroxide, right? Even though they figure out that the iron is really impactful for the activity, right? So to mimic that previous results that people already gave, I prepared that 0.1 ppm iron dissolved electrolyte after purification of the potassium hydroxide, since I would like to control the amount of the iron during that water electrolysis. And I can also mimic that the result people already observed that almost 10 years that there is no any activity decay during that the 1 hour, right? And the remaining thing is which atoms can be dissolved during that the reaction, right? So I discussed that the iron nickel hydroxide with the iron purified electrolyte, then activity goes very quickly and figure out that there is significant dissolution of the iron, right? The nickel is the really stable. Please keep in mind this is the log scale order, right? What about that iron cobalt? Very similar trend has been observed, right? The activity goes very quickly, and the huge dissolution of the iron has been confirmed compared to the cobalt itself, right? So this is a really interesting features that there is a huge dissolution of the iron is incorporated with the activity decay, right? The remaining thing is I'm really curious about what happened during that the reaction condition, right? In when there is iron in electrolyte, but unfortunately we cannot distinguish between the iron, right? Because there are two types of the iron is already incorporated. One is the electrode and the other one is the electrolyte. So I prepared that to distinguish those two iron with the different masses. So I designed that isotope experiment, for example. So I prepared that the electrode with iron 56 and electrolyte with the iron 57 and measure that how the iron 56 can be please keep in mind iron 56 is incorporated as an electrode at first and monitor how it can be dissolved out, and the data shows that the data is almost identical with the case what we discussed about when there is no iron in the electrolyte, right? So this is a really striking because that even though that the activity is maintained, the iron in the electrode can be dissolved out very quickly during just 10 potential cycles, right? So to capture what happened during that system, I designed that the another experimental the cases. So if I prepare the iron 56 in electrode and there is no iron in electrolyte, and during the corona measurement, I quenched that the electrode end to monitor how the amount of the iron can be exist in the electrode, right? And this is the amount of the iron can be absorbed during that system. It shows that the striking trend that activity is followed by the amount of the iron in the electrode, right? Surface. And to figure out what happened when there is iron in electrolyte, I prepared the 56 iron in the electrode and I prepared the 57 electrolyte and do the same way. The activity is really maintained, right? And the striking feature is that since please keep in mind that this is the iron in electrode, right? So the initial iron 56 from the electrode can be gone very quickly, but we can observe that there is iron from the deposition from the electrolyte. We can confirm that iron 57 can be confirmed in the electrode. So total amount of that iron in electrode can be maintained, which is the very good correlations between that the activity trend, right? So the remaining thing is we confirm that there is a very interesting features, right? Before that, people discussed about that when there is no dissolution, the system is very stable, and when there is a dissolution, the system is unstable. However, as we discussed that, there is a huge change over the reaction, right? There is a huge dissolution and deposition, but the activity can be maintained. So to distinguish is what happened between that when there is no dissolution, we call it as a dynamic stability, right? And the remaining thing is where the active site is, right? So I would like to really interest things about, all right, I conjecture that Fe is the active site, and why the iron nickel is so important compared to the just iron, right? So I'm really curious about, is there any chance to tune that weight absorption energy? Please keep in mind that we already discussed about that. The intermediate absorption energy is the good descriptor for the activity in electrocatalysis, right? So we call it as a thermodynamic concept. So at the beginning, I'm really curious about what happened for the by just a small amount of the iron can change that the overall the thermodynamic property. So, but it is really challenging, right? Because that, please keep in mind, we only measure that the activity, right? However, please keep in mind the activity can be calculated by the how many active site times activity per active site, right? But we don't know actually, right? In general, people assumes that the number of active site is the fixed value. So in general, people just directly correlate between activity and the thermodynamic, the delta G parameter. However, it is not true in OER because we already figured out that there is a huge change during the reaction condition, right? So I would like to jump into the hydrogen evolution reaction because at the time I aware that our group already discussed about that hydrogen evolution reaction is affected by the OH adsorption, right? Please keep in mind that we already discussed in HER, right? So I compared that what happened when there is contaminated by the iron. But the striking feature is that the HER activity is not changed, which means that the thermodynamic parameter cannot be changed during the HER, which is a direct evidence that I confirm that the thermodynamic parameter is not changed, not heavily changed by the incorporation of the iron in the nickel and the cobalt. So the remaining thing is, what about that the number of active sites, right? So to figure out that, I prepared that the several types of the different electrolyte and different substrate, and I confirmed that the activity is directly correlated with how many atoms in the surface during that reaction condition. So please keep in mind that the number of dynamic iron species can be quantified by the quenching during that the reaction condition. So based on this, we directly confirm that it is really important, right? Not only just control the thermodynamic parameter, but also how the active site can be work as a active site because there's a huge dissolution. So this is the summary, right? In general, people discuss that the number of active sites is a constant, but I would like highlight that when there is a huge reconstruction, we have to think about what happened during that the reaction condition. And this is the one very nice example that there is a crosstalk between the electrode and electrolyte. So I propose that there is a equilibrium between that electrode and electrolyte in the iron species. And I do not want to go into detail, but please keep in mind that there is the bunch of the opportunity to control the activity, right? If the system is the harsh condition. So this is the summary that I would like to discuss for the alkaline OER. Even though I discussed that the OER, but the focus that I would like to discuss is that the number of active sites is not the not the constant value anymore in the real condition. So even though I would like to highlight that we definitely focus on to the thermodynamic parameter, right? The delta G, because this is really important to determine by determining for the turnover frequency. But we also figure out that how to make it the active site as a active site without dissolution. And this is the one summary that how to tune the active site. And and then we would like to also discuss about that the certain important issues about oxygen evolution reaction as a final topic. So we discussed about that the activity and stability discussions for the design principle for OER. But not going into detail, I would like to highlight that the very important features that we have to do to keep in mind in general, the discussions for the OER, right? So please keep in mind, we only measure data current, right? The certain current depending on the potential. But in general, we only figure out that this current is coming from that Faraday reaction. What the Faraday reaction means in OER, that is the O2 production, right? So just aware that if you get the higher the current, it can be directly related to the higher OER, the current, but the real is not true because as already mentioned that we have to think about that there is a possibility of the non-Faraday reaction, right? For example, charging or discharging behavior. And furthermore, I would like to discuss and highlight once again that the side reaction, that this is the very important, right? Because that we don't know that where the electron comes from, right? We only measure how many electron can be transferred, right? And we conjecture that it is coming from that oxygen evolution reaction. But if there is a possibility, we definitely figure out that is there any the impact for the real the activity is. And what about that the most striking feature is that the dissolution current, right? Because there is a huge dissolution. So if there is electrochemical dissolution, we have to consider how many charged electron can be extracted during that the system for the corrosion, right? So not surprisingly, if you would like to discuss about the Faraday current, the easiest, I'm sorry, it is not easy way in general, but the most direct approach is to quantification of the oxygen production during that reaction condition. All right. So the easiest and the direct method is to confirming for the oxygen concentration during the reaction condition. And so there are lots of the way. The first one is you just measure, right? You just measure the volume of the oxygen, for example, the balloon or something like that, or just to quantify that the gas chromatography to quantify. And also you can also utilize that the mass spectrometry, how many oxygen can be dissolved, right? So anyway, you need a gases product analysis, right, to directly confirm that how many oxygen can be transferred, right? So I would like to highlight once again. So the current is a good metric to estimate that the reaction, but if there is any possibility to exert that the electron transfer, you definitely confirm that how many oxygen can be really synthesized, produced during the process. So this is the direct comparison and direct validations about the real chemical reaction. And what about the others? You just confirm that the Faraday reaction the different way, because please keep in mind that this is the direct confirmations about oxygen gas, right? The volume, by measuring the volume and by measuring the concentration, by measuring the real quantity, right? And what about different way? We already discussed about that, the rotating ring disk electrode, right? So when we generated the oxygen in the disk and when we apply that the potential for the oxygen reduction reaction, right? So for example, the potential below the ORR, the onset potential, right? Then we can quantify that how many oxygen can be really produced during the oxygen evolution reaction condition, right? That this is the one good way. And not surprisingly, this analysis can be extended to other systems. For example, when there is a chlorine in the electrolyte, the chlorine evolution also be overlapped with the oxygen evolution reaction, right? So if you directly measure that the amount of the oxygen reduction by the rotating disk electrode method, then you can directly compare how many OER and CER. I'm sorry, the different way. The lead one shows the CER. So how many OER and CER can be evolved during the reaction condition. So the electrochemical method can be also utilized to quantify that side reaction when you measure the oxygen evolution reaction. All right. And is there the further impact for the side reaction? Yes, it is, right? Because we would like to only discuss about that water oxidized to produce that oxygen, right? But there is a different trend, right? What the different trend means that there is a certain possibility to produce that the water to hydroxide. Please keep in mind, we already discussed about oxygen reduction to produce the either water to H2O2, right? The similar way, the water oxidation can be possible to produce either oxygen or hydrogen peroxide, right? And what about the ozone, right? So there is a possibility, right? I'd like to say that. So this is I'm sorry, this is the 2025, not the previous one. There is 죄송합니다. 이거 2025년도예요. So it is not a 2015. I'm really sorry that this is the 2025 very recent paper. And so there is the way, right, to confirm that the amount of the hydrogen peroxide and ozone. But the good thing is that the proportion is really negligible. So in general, we do not aware of this idea, but there is still theoretical possibility, right? So please think about how to quantify that the actual Faraday reaction occurs. And what about the possibility for the side reaction? As I already discussed, the dissolution, right? So not surprisingly, recently this is the very hot area, right? To quantify that actual dissolution during the reaction. So we can monitor, right, the dissolution during the reaction condition that quantify that if you quantify that the side reaction, then you can get that the true value, right? So if you just monitoring that the dissolution, this is really good for not only quantify that the actual OER occurs, but also you can monitor the activity and stability as a trend for the discussion, right? So I do not want to discuss in details about how to measure. We would like to utilize that the ICP mass. To make a long story short, ICP mass is a really powerful technique, and there are two terms, right? ICP mass, right? And for example, there is a GC mass or LC mass, for example, right? There are several terminology looks like, right? So what about that the pre-term shows that how to treat the samples before the mass spectrometry, right? So all the system is exactly, we would like to utilize that the mass spectrometry, and the pre-version, the pre-term shows that how to treat the sample, right? So ICP means that the inductively coupled plasma. So we would like to apply that the really high temperature over 6,000 degrees C. Then if you apply this the temperature, almost all of the samples can be atomized, right? And then if it is atomized, we definitely just transfer to the mass spectrometry. Then we can confirm that which element, because that each atom shows the different mass, so we can distinguish that which atom, and we also confirm that how many of the atoms can be exist during that system. So this is really the straightforward system to quantify that ICP. So actually, not surprisingly, our group also has our own ICP mass for the electrochemical system. So we can routinely utilize this what happened during that system. And this is the recent the publication results from our groups that we can monitor the dissolutions about the iridium during oxygen evolution reaction, right? So we can easily, frankly, not easily, it's not that easy, but we can monitor the actual dissolution of the element during the reaction condition. So the ICP mass is really popular recently because people would like to discuss about the stability trend in detail, right? So this is really powerful, not just for atomic dissolution. People would like to utilize that ICP mass because not only atomic dissolution, we can also monitor the particle detachment from the support materials, right? So this is the one of the good example, which is published very recently also from Thomas Harmie group in Stanford, and they figure out that there is a huge the detachment of the gold nanoparticle during that CO2 reduction. So we can confirm that the detachment of the particles during that the reaction condition, right? So finally, I would like to shortly mention about what happened for the OER. Please keep in mind that what is the reactant? The reactant is the water or OH minus, the liquid phases, right? And what about the product? Product is the oxygen, right? So not surprisingly, the OER is the gas bubble production. So at the very beginning, there is a small bubble on the surface. Not surprisingly, if you increase the current or if you apply more, the oxygen bubbles get increased, and certain period of time, it can be detached, right? Which means that the oxygen bubble may affect that the overall current, right? So you have to do very careful analysis when you discuss about OER or HER. In other words, that the gas bubble production reaction, this bubble also affected the overall activity. And also it looks like a stability trend, right? So this is the really interesting data, right? So at the very beginning, it is a really good activity. And if you discuss that the long-term operation, it looks like activity is gone, right? So people think about that this material is not good for the activity, right? Not good for the stable. But please keep in mind there is a possibility that the oxygen gas, the product gas, can affect that the overall the activity, right? And so this is the very interesting feature. So this is the right. So this is the initial data, the black curve, right? And the blue one shows that after 30 potential cycles. So in general, we just think about there is an activity decay like this. But please keep in mind, if we remove that bubble, then the activity looks like can be a certain activity can be the replenished, which means that we have to do very careful approach, right, to discuss about that activity and stability by the impact of the bubble. Not surprisingly, people would like to develop that the method how to distinguish that the bubble effect. So this is the ridiculous way, but this is the really straightforward, right? So if you just apply that the ultrasonication hole near the electrode, then we can easily remove that bubble, right? So, for example, the rotation can also helpful to remove the bubble. And if you apply the sonication, the activity is much better. Why? The oxygen bubble can be easily detached, right? And what about that applying that vacuum to remove that the oxygen bubble? Then you can the floating electrode is the bubble base a bubble removing base removal by the vacuum. So the overall current is much higher compared to the general RDE measurement, right? And very recently, we figured out that the oxygen bubble can make lower activity. And is anyone think about that? Why? Actually, people just think about, oh my gosh. So at the very beginning, the surface is really open, but if there is a bubble, right, then it covered that a certain surface, right, the active side. So people in general think about that when there is a bubble, it just covered that a surface, the active side, which means that the activity decay is coming from that decrease of the active side, which means that increase of the charge transfer resistance, right? But not surprisingly, it is also be published very recently, right? 2025, almost 2 months ago. Not 2 months ago, actually, just 1.5 or 1 month ago. So this is a really interesting data, right? And so what happened for the bubble for the lowered activity? If there is a bubble, there is a huge impact for the solution resistance, right? So please keep in mind that even though it looks really simple, we cannot fully understand yet what happened and what the impact for the activity, right? So this is the a really good model study that this bubble can retard that ion transport, so it can make a lower activity. So I would like to highlight once again, there is a striking bubble issue. So we have to think about when you design or when you analyze your samples, the bubble issues also be discussed as a major impact. 그래서 오늘 우리는 OER 주로 살펴봤고요. 그래서 OER에서 제가 살펴보고 싶었던 내용은 사실은 굉장히 지금 핫한 분야이기 때문에 뭐 어떤 제가 정답을 드릴 수 있는 부분은 아니고 제가 오늘 말씀드리고 싶었던 것 중에 하나는 OER 파트를 설명하면서 일반적으로 우리가 액티브 사이트라고 한다라는 게 그죠? 표면적이라고 하는 거 그러니까 죄송합니다. 우리가 촉매를 만들었을 때 내 촉매에 액티브 사이트가 몇 개 있냐라고 할 때에는 그 촉매 표면적에 그다음에 그 표면적의 액티브 사이트 덴시티를 곱한 값이고 그래서 그 값을 우리가 항상 컨스탄트로 생각을 했다라는 거죠. 그죠? 액티브 사이트가 몇 개고 그러니까 결과적으로 얘를 나눠주면 커런트 덴시티가 결과적으로 우리가 델타 G 값을 나타낸다라고 생각해서 기존의 많은 연구들이 성능이 높으면 왜 성능이 좋아질까를 연력학적 파라미터에 초점을 맞췄다면 이 부분은 사실 굉장히 중요한 거지만 굉장히 많은 리액션에서 그 촉매들이 굉장히 녹아나고, 그죠? 혹은 다시 재등착되기도 하고, 그죠? 혹은 변형되기도 하기 때문에 얘를 단순하게 우리가 컨스탄트로 생각할 것이 아니라 얘가 주변 환경, 그 주어진 환경에서 얼마나 이펙티브하게 존재할 수 있을지를 조금 디자인하는 파라미터의 컨셉이 필요하다라는 걸 예로 드리고 싶었고요. 그 다음에 우리가 OER에서 특히 중요하게 생각해야 되는 건 OER에서는 굉장히 사이드 리액션이 많이 일어날 수도 있잖아요. 굉장히 높은 포텐셜이기 때문에, 그죠? 사실 높은 포텐셜이라서 우리가 일렉트로라이트를 분해하고 있기 때문에 우리가 그 포텐셜 내에서 상당히 다른 물질들이 분해될 수 있다. 특히 뭐 대표적으로 그 물질 자체, 전극 물질 자체가 분해될 수도 있고, 그러면 코로전이 될 거고, 그죠? 아니면 뭐 다른 Ni온, 예를 들어서 클로린 이온이 산화되면 클로린 이볼루션이 일어나기 때문에 내가 실제 측정한 커런트가 실제 OER이 아닐 수 있다라는 거, 그죠? 그래서 어떻게 내가 페라데이 그 리액션의 컨트리뷰션을 알 거냐? 뭐 제일 쉬운 방법, 물론 이것도 쉽지 않습니다만 그냥 O2가 얼마나 생성되는지를 직접 모니터링하는 게 제일 쉬운 방법이 되겠죠. 그러니까 쉽다기보단 가장 다이렉트한 방법이 되겠고 근데 오트로 확인할 수 있는 방법도 뭐 이렇게 볼륨을 측정하거나 아니면 뭐 농도를 측정하거나 할 수도 있지만 우리가 전기화학적으로 RRD로 활용할 수도 있겠다라는 점 설명드렸고요. 그죠? 그 다음에 사이드 리액션이 사실은 굉장히 다양할 수 있다는 거예요. 그죠? 사실은 물이 산화돼서 H2O2를 만들 수도 있고 오존을 만들 수도 있거든요. 그죠? 물론 그 양 자체가 그렇게 많지는 않아서 크게 신경을 쓰지 않아도 되지만 최근 2025년도에 ACS 카탈에 보고된 걸 보면 그것도 역시 RRD 방법으로 할 수 있다라는 보고도 있긴 하고요. 그 다음에 역시 아까 말씀드렸던 그 물질 자체가 코로존 되는 거 최근에 굉장히 주목받고 있기 때문에 이 부분도 한번 생각해 볼 필요가 있다라는 말씀을 드리고 마지막으로 그 다음에 이제 버블 문제겠죠, 그죠? 물이 산화되면서 결과적으로 옥시전 버블을 만드는데 그 옥시전 버블이 표면에서 계속 빨리빨리 떨어지는 게 아니라 일정 사이즈 이상이 돼야 떨어진다라고 보고되고 있거든요. 그러면 그 일정 사이즈까지 도달하기 전까지는 표면에서 원래는 표면적을 가리기 때문에 성능이 줄어드는 것처럼 보인다라고 했는데 최근 연구 결과를 보게 되면 실질적으로는 표면적을 가리는 효과보다는 이런 버블이 있으면 이온의 이동이 제어돼서 그러니까 줄어들어서 그죠? 그래서 그런 그 뭐라 해야 되지? 성능이 감소하는 그런 현상이 나타난다라는 보고도 있습니다. 그래서 결과적으로 우리가 지금 관찰하고 있는 현상이 우리가 직관적으로 생각하는 것 이외에도 그죠? 이런 바깥의 파라미터의 영향을 많이 받기 때문에 그런 부분들을 좀 고민해야 된다라는 것을 우리가 살펴봤습니다.